Hi everyone, my name is Dennis Madsen. I'm from the University of Basel in Switzerland, from where I'm presenting our paper, Learning Shape Priors from Pieces. The shape priors that the title is mentioning is within the domain of linear point distribution models. This could for instance be models of anatomical structures such as the femur or any other structure which can be discretized to a set of points. Let us first have a brief look at how to create a point distribution model from complete data. First, we establish point correspondence in our dataset such that all shapes have the same number of points. Then the data is aligned to minimize rotation and translation within the data. Finally, we can compute a low-rank approximation of our dataset to obtain a parametric model with which we can synthesize all kind of data of the given object. So what problems are we facing when our dataset goes from complete data to partial data observations? Using partial data observations to build statistical models is especially useful within the medical domain. So the first problem we are encountering with partial data is possibly large uncertainties in the correspondence. If we have one full mesh and we're establishing point correspondence to a partial mesh, the correspondence can easily be identified in areas with high local curvature. But on smooth surfaces, there could be a whole range of correspondences, which is the correct one. Using any of these 5 different correspondences for the single point would change the eventual deformation a lot. Also note here that we need some robust way to compute our low-rank approximation, as we do not have full knowledge about all shapes in the dataset. A second problem is dataset alignment. If we only have a part of the mesh available, we could align it to the most similar one in the dataset. We could also align everything in the dataset to this one part. We could also try to estimate its global scale from some kind of regression based on the other entries in the dataset. From this overview, the last approach seems more reasonable, but the problem is now, how do we find the completion of this mesh? So at first, we can discard all observations with missing values. Alternatively, we can use a more robust way to compute our low-rank approximation, for instance by the use of probabilistic PTA. This will try to complete the data matrix iteratively, but will in general not optimize over the rotation and translation parameters. Finally, we could also try to complete the data before using any learning algorithm. This is known in the Bayes setting as data imputation. If we impute the data before computing the low-rank approximation of the matrix, then we can solve the translation and rotation in closed form using Procrastinus analysis. So from the motivation here, it sounds like imputation is the way to go. So let's look at some different imputation methods. For the first method, we can compute the mean or the median of the meshes where the entries are not missing. This, however, directly assumes that we know what is missing, and even worse, it will bias the variance towards 0. Alternatively, we can perform single imputation by regression based on the data entries that are complete. This, unfortunately, has a tendency to overestimate the correlation in the final model. And before performing the imputation, we implicitly have to specify what points are missing. Lastly, we can use multiple imputations. So if data is arbitrarily missing, we can use an MCMC method to create multiple imputations. This can be done by simulating draws from a Bayesian predictive distribution given some partial data. So an important aspect to note here is that ideally, each of the multiple imputations can have different correspondence assumptions. So by drawing multiple imputations, we can therefore assess the uncertainty of the missing part. As we're able to complete the missing part, we can use this completion for the alignment procedure as well. So let us now look at how this multiple imputation can be implemented in practice. So given a reference and a target surface, non-rigid registration can be seen as finding this deformation U that will make the reference surface explain the target. So by changing the deformation field U, we can explain different shapes of the same shape class using a single reference. But note here that we need some prior information on the deformation fields for the completed registration of the partial data to still look some kind of like femurs. So if this is not the case, we might end up that the reference is completely collapsing in the area of the missing data. So traditionally, non-rigid registration is formulated as an optimization problem, where one will end up with a single point-to-point estimate by minimizing the distance between the target and the reference. So instead, we reformulate the registration problem as Bayesian inference. So given a target surface gamma t, we're searching for the posterior distribution of deformation fields, which will explain this target surface. But for this, we already need to have some prior assumption on the deformation fields U. So at the core of our framework, we make use of Gaussian process morphable models to define our deformation space. A GPMM is a generalization of the classical point distribution model, where deformations can now be modeled as Gaussian processes. So Gaussian processes make use of kernels to define deformations. An example of a deformation function is the basic Gaussian kernel. So this here will give us a continuous Gaussian process model, which can then be discretized to obtain a parametric low-rank approximation. With this here, we can easily express any surface by setting the alpha vectors, which follows a standard normal distribution. So now, instead of finding the posterior distribution of deformations U, we can instead estimate the posterior distribution of alpha parameters. Unfortunately, we cannot analytically compute the posterior distribution of surfaces with shifting correspondences. But what we can do instead is to compute the unnormalized density value for any shape described by alpha with a GPMM model. So essentially, we avoid computing the normalization constant, and instead we compare different alpha vectors in order to estimate the posterior distribution. For this estimation, we make use of the well-known metropolis-hastings algorithm, and in our ECCV 2020 paper, we showed how this posterior distribution can be obtained efficiently with the use of an informed proposal distribution. So now, compared to the standard way of creating a point distribution model, we only have a few additional steps. First, we need to define our missing data model, in this case a GPMM. Then, for each mesh in our dataset, we compute its predictive posterior distribution. Then we draw L number of imputations from each distribution. Then we can align all the sampled meshes. And finally, we can compute a low-rank approximation of the data matrix, which now contains M times L columns. Now let us have a look at a practical example. So here we have 10 partial femurs from which we want to create a point distribution model. For this, we need one complete reference shape. Then we define our prior information as kernel for the Gaussian process and construct our Gaussian process morphable model. So here we have an example of a target mesh in red. We can then compare how the mean and the maximum and posterior solutions compare to the ground truth shape, which is shown in orange. And we also see how the random samples in black, they nicely explain the ground truth shape. What we still need to do is some evaluation to see if we can actually compute good models from only partial data. To do so, we make use of the 3 model evaluation measures: generalization, which describes how good a model is to explain data outside of our dataset, and specificity, which evaluates how similar the generated shapes from the model is to the dataset that it was constructed from. And the third measure is compactness, which we'll not focus on here, as we're more interested in having models which can generalize well to new data, but also remain within their shape space. In our femur experiment, we construct femur models from an increasing amount of samples from the posterior distribution, so the parameter L. The different models here we compare to the model which is constructed from the complete ground truth data. In this plot here, I just included a few of these models. In the paper you will find more. But what we observe is that we need 5 or more samples from each of the posterior distributions to get the best generalization ability. And in fact, we see the same for specificity, where we can also see that having 5 or more will give more or less the same specificity as the ground truth model here. In the paper, you will also find some additional experiments on synthetic hands, and we also qualitatively show how it's possible to create a skull model when only partial data is available. So to summarize, we first introduced the main problems concerned with creating point distribution models from partial data, this namely being the uncertainty in correspondence and the alignment of partial data. Our solutions to these problems is to analytically define a data model using the GPMM framework and use this model to estimate posterior distribution of completions for each partial data observation. The alignment can then easily be done based on the imputed data. Our code and data used for the synthetic data examples is available at GitHub. And with that, we are at the end of the presentation, so thank you very much for listening.